Hello everyone, welcome to lecture 5 of week 3 of the course Power Network Analysis. This lecture is also going to be the last lecture of week 3 in which we will continue our discussion on the module Synchronous Generators. In this discussion today, we will discuss or understand a very interesting topic which is known as economic dispatch, and this economic dispatch, it helps ensure minimum cost of generation, helps maintain the economics, which is one of the good attributes of a good power network, which we discussed or learned about in the first lecture itself, which was the introduction to the course. And what is the effort involved, what is the mathematics involved behind maintaining this system economics while dispatching generated electricity to the loads is what is going to be all about today's discussion. This discussion which we'll have, it will build up on the previous lecture discussion, which was extensive enough about what would be the real power expressions, reactive power expressions, how do we control the flow of real power and reactive power from synchronous generators to the respective power network or to individual loads. And in this entire discussion of economic dispatch, we will mostly be focused about the real power aspect. So controlling aspect we have seen in the previous lecture. Basically, the real power control comes from the turbine action or prime mover action. And what is the economics behind this real power transfer is what is going to be the prime focus of discussion in this particular lecture today. So in a practical network, we usually don't have single generators. We have multiple generators. Some of them happen to be synchronous generators, and some of them could also be renewable based, non-synchronous based machines. For example, like solar PV power plants or wind generators, they are not synchronous based machines. And these generators, they are placed at different locations in the power network, and often these locations are not the same locations where the loads are present. So basically, there's a huge geographical disparity between the locations of the generators and the loads, and that's where the role of transmission power network or transmission network comes in to sort of balance out this geographical disparity. These different generators, they can have different operating frequency. Their operating frequency is going to be different because the philosophy might be different, the technology may be different, the type of fuel which is used to drive the synchronous generator might be different. So depending on what type of synchronous unit we have, it could be a hydro-based plant, a nuclear-based plant, thermal, or renewable-based resources based on solar, wind, and biomass. And each of these different technologies, fuel mix, type of the synchronous generator brings in or has its own economic aspects. So setting up a power plant has its own capital cost involved. Operational aspect involves salaries to be paid to the operator or the people who are maintaining the plant. So every power plant, it tends to have its own investment cost, capital cost, and its own operational or running cost. Depending on the type of plant, specifically for hydro and nuclear power plants, where lot of effort is needed to set up or bring up those plants. For example, in hydro power plant, lot of geographical area is needed for creating the water reservoir, and then building the reservoir, the dam itself is itself it's an engineering marvel in itself. So it involves lot of manpower, lot of capital investment is required. Similar goes for nuclear power plant. Lot of safety perspectives, safety design goes into setting up a nuclear power plant. So often these hydro and nuclear power plants, the capital cost is very high. And since the fuel which is being burned in a hydro, it's just the flow of water, or nuclear based reaction, which is comparatively cheaper than the thermal power plant. So the operational or running costs are also low. There's another reason why nuclear power plants tend to have low running or operational cost, because most of the nuclear power plants, even in India, they operate as based power plants. That means their power generation output doesn't change. Once they are commissioned, usually nuclear power plants, they tend to generate the same quantum of power under steady state conditions throughout their lifetime. The reason why nuclear power plants generally act as base power plants, because perturbing or controlling nuclear reactions is obviously not as easier comparing to controlling flow of steam or flow of water through the turbine to drive the prime mover or the generator. So that's the reason why the control perspective or the safety perspective, I would say, from the safety operation perspective, nuclear power plants tend to behave as base power plants. And if a element is operating at the same quantum of power, most likely its wear and tear would be lesser, so maintenance cost would be lesser and hence operational cost would be lesser. On the other hand, thermal power plants, they are not as capitally investive compared to hydro and nuclear, reason being the small geographical area which is needed often. So the capital cost involved is comparatively lower, but then operational cost is very high because of lot of rotating or moving devices being placed. Typically in a thermal power plant, either we would use the fossil fuels, the coal or the gas to be burned in the boiler, which in turn heats up water, which converts to steam, and then the steam drives the prime mover to sort of drive the synchronous generator. So lot of wear and tear is involved, lot of transportation is involved, and that's what leads to higher operational cost in thermal power plants often. On the other hand, renewable based generation or sources like solar and wind, the capital cost is also low and operational cost is also low because of less wear and tear involved. And more importantly, in renewable resources, the uh, availability of fuel itself is either wind or solar radiation, which are naturally available, and hence no additional setup is needed, unlike in hydropower plant where a dam needs to be placed. In solar and wind turbine or generation, the corresponding effort required to set up is comparatively lower, and also the operational cost is lower. So given a network which has these different types of technologies of different types of synchronous generators in place, eventually all these synchronous generators, they are essentially driving the network load. If the load would not have been there, then there would not have been any need of power network, there would not have been any need of generation, no need of a transmission network. Now that is point number one. Point number two, this load often tends to be having variation. So what is shown over here is the beautiful duck curve. It's the source of this particular duck curve. It's also given here on this link. So basically it is the predicted load for 2024-25 for a typical day, and it also has certain curves for the previous years for some particular resource or location, which can be seen in this particular link. What is important to observe here is this load which we are experiencing across 24 hours, starting from 6 a.m. in the morning till 5:55 a.m. on the next day. The load is not a constant, doesn't have a constant profile. If the load would have remained constant, probably then also the effort needed to maintain system economics would have been reduced. It would not have been as substantial. Now, the load, why does it have variation? It's pretty normal. It's pretty obvious. Depends on how we live our lifestyle. So typical human beings, they tend to get up at 6 a.m., get ready for their day, get ready for their work or school or office or college, go out and do their daily course, and then around, so typically when people are at their offices, the corresponding domestic loads tend to consume lesser washing machine, lesser heating, lighting load are needed because it's 12 noon. And again, as evening comes in or sets in, lightning load tend to go up, people tend to return back to their homes or cottages, wherever they stay, and in the evening we need light, so the power or the load again tends to go up around evening. And once post dinner, usually normal human beings tend to sleep, so again after 12 noon or so, or around 8 or 9 p.m., the curve tends to go down, and again from 6 a.m. it tends to go up. So that's how a typical load for a typical day or for a typical load or for a community or a society or a city tends to have two peaks and one duct or one flat lower profile, and if we try to fit in, it looks like a duck curve with the head of the duck representing one peak, the tail representing other peak, and the belly of the duck representing the lower bottom half. And this is not just for one day. The overall load or aggregated load in a network also tends to have annual variation. Typically in extreme summer and winter weather, the power consumption goes up. For summer, it's the consumption for cooling. For winter, it's the consumption for heating. While during spring and autumn season, the weather is pleasant, the corresponding aggregate load requirement tends to go down. So daily load curve will also typically follow a duck curve if you were to plot it for a particular city, community, society, or a country. So the question is, if the load itself is not constant and individual aggregated loads tend to have this variation, how do we ensure our generators are operating at minimum cost, that is economics is being maintained, and how do we ensure that profits are being made by the generators, because every entity would tend to make profit to the extent possible. So that's where the idea of dispatch comes in, or economic dispatch comes in. Total generation must always meet the demand or the load. In addition to meeting this demand, to ensure system security, we also expect, or it is also expected as an operator, network operator, to also ensure some generation margin which is over and above the committed generation which would meet the demand. We call this to be a spinning reserve or a rotating reserve. More details would come as and when we venture through the upcoming discussions, specifically in stability analysis and power flow analysis. So over and above the scheduled generation to meet the demand, just some generation margin is always been committed in a power network to sort of address any contingent conditions such as load changes which might not have been anticipated. So typical generation dispatch philosophy one would think of is that, oh, we have different types of units of different efficiency, so let's try to prioritize or operate the highly efficient units first, so that during light loads these highly efficient units deliver power to these loads, and as and when the demand goes up, lesser efficient units or costlier units are brought online. The problem with this conventional thought process is that it might not always lead to the least cost of generation. By least cost of generation, I am not meaning individual cost of generation. The power network consists of several generators. When I talk about system economics, it is the total net cost involved in generating power from all these individual units. Minimizing one such generation unit cost will not suffice. If economics has to be maintained from the system perspective and fairness is to be ensured, one should always bother about the total cost involved in generating power in a given power network and not the individual units. So this conventional philosophy will have this problem, and that's where economic dispatch comes in, which is a very integrated, beautiful, optimized way of ensuring least cost of power balance between generation and loads. Specifically from our discussion of economic dispatch, we'll focus only on thermal units because their operational costs are comparatively higher, capital costs are moderatively lower, while ensuring system security and reliability, wherein this one of the ways of ensuring the security is through maintaining a spinning reserve or sufficient generation margin. Again, for simplicity of our discussion, we will not consider this notion of spinning reserve. I'll briefly touch upon the notion of spinning reserve as and when the right time comes in upcoming lectures. And depending on the time frame in which this power balance is to be maintained, now if we try to maintain power balance between generation and load at 9 p.m. in the night, then since I am trying to maintain optimization only for one time snapshot, I would call that to be a static economic dispatch, which may make sense for that given period of time, but in practice, the load keeps on changing, and that's where the beauty of economic dispatch comes in. So if we try to ensure power balance while maintaining security and reliability for a time period, let's say for 24 hours, then that would be called as a dynamic optimization based economic dispatch. This is just for the sake of discussion. For our sake of discussion, we'll focus on a static framework for economic dispatch for simplicity of discussion. So Question is, why do we need economic dispatch only for thermal units? As I have already mentioned, nuclear units, they mostly operate as base plant units from the perspective of safety reasons and from control complexity involved in controlling these plants. Hydro units have low operating cost, in fact, close to negligible operating cost with high ramp up and high ramp down capability. Now, what is meant by ramp up and ramp down capability? Suppose there is a generator which is generating, let's say, there is a generator I which is generating PGI at a given instant of time, and as the load is varying with time, so let's say at T plus delta T time, the load earlier was PDT, and at T plus delta T, the load has changed to PT plus delta T. The load could have increased, could have decreased. Since total generation has to follow in the entire system demand, it is expected that the generation of ith unit at T plus delta T might be different from the generation at time instant T in order to maintain the balance of load at the different time instances. Now, when the generation tends to change, that means some control action has to come in. So, basically real power control has to come in, which means that the turbine has to respond so that the corresponding generation output, specifically real power output, can change. Now, this change which happens, it has to happen between a time instant or duration of delta T. Generation might go up, might go down, depending on whether the load goes up or go down accordingly. Often our power plants, specifically thermal power plants, since they have got lot of rotating devices involved, in the sense there is a boiler involved which is having its own mechanical inertia. Temperatures in a boiler cannot change instantaneously. Boiler takes time to heat up and also to cool down. So, if the boiler is taking time to heat up and cool down, the corresponding steam exchange would also take up time, and as a consequence, the turbine action will also take time. On the other hand, for hydro units, the hydro units power control will just be regulated through flow of water. So, if you open up the valve in a hydro turbine, more water gushes in, turbine rotates at more speed and hence more power is developed. Since the water is involved there, controllability is faster, and that is what leads to ramping up and ramp down. Ramping up essentially meaning generation increases from its previous instant of generation. Ramp down means generation goes down from its previous instant of generation. Hydro units, the controllability is faster, the response time is faster, and hence the change in generation can happen at a faster pace. Whereas in thermal units, because of boiler, turbine, the generator itself involved, which have their own mechanical inertia to change in temperature and movement or rotation, thermal units tend to have very slow ramp up and ramp down capability. Their operating costs are also higher because of transportation, maintenance involved. And the important part which is critical here is because of this slow ramp up and ramp down capability, since the load is not stagnant, and specifically things become much more difficult when we have these renewable resources which are non-conventional sources. Their generation pattern depends on weather, solar availability or wind availability. So, if the generation also is changing from renewable perspective, there has to be some generator which should act as balance or buffer for this mismatch in between generation and load as well as change in load. So, difficulty is with slow ramp up or ramp down capability, thermal units have a difficult time adjusting themselves while catering to system power balance and security. And that is where the dynamic economic dispatch makes further more sense, which we will not consider for our discussion. The idea in dynamic economic dispatch is we plan well ahead of time rather than focusing on a specific time of interest, and we would be prepared economically with our thermal generation schedule that would ensure economics and security and reliability while meeting the system demand. When we are talking about economics, it makes sense that there has to be some quantification for this economics behind power generation. So, often in thermal unit perspective, each of these units, their power generation, which is net output P megawatt, it is associated or linked with some fuel cost or some cost which is usually obtained from the heat rate curves of the boilers and the corresponding combined boiler turbine action. We tend to assume this cost to be a hourly cost for the sake of our discussion, and it need not, this cost curve which is being shown here, the cost being on the y-axis, the generation being on the x-axis, this cost need not pertain to instantaneous cost for sake of simplicity, again for sake of discussion. We will be assuming this cost to be a hourly cost, means the generation is not changing. For simplicity of discussion, again practically it would definitely change. The generation is not changing for a given time slot, which is typically 1 hour, and hence the cost associated in generating that particular power is also constant, and that's where the hourly costs are involved. Typically, out of this total power P which is generated, around 6 to 2% power is consumed as auxiliary power for pump action, condensers, rotor excitation, etc., etc. 94 to 98% of net power P is observed as the gross output. And usual cost characteristics, they are not smooth, they are not continuous, they are not differentiable, which we will not be bothered about as of now. We'll assume ideal conditions where the cost characteristics are smooth, and the non-ideality or non-practicality comes in, or practicality comes in, because generators, typically thermal units, they don't have continuous mode of operation. As temperature changes from few hundreds of degrees to thousands of degrees, the corresponding power output change with respect to boiler input or fuel input, which is the coal or the gas, the corresponding power output has a nonlinear relationship, and that's what we call as valve point effects. The moment we open up the turbine valve for more steam to flow in, or close the valve for the steam to lesser flow in, the corresponding output change is not linear with respect to this valve change effect, which in a way results in burning of more fuel in the boiler or lesser fuel in the boiler. So practical characteristics, they tend to have discontinuities because of nonlinear response. And from the safety perspective, every generator has a minimum generation limit and a maximum generation limit. Now, the minimum generation limit, it typically comes from the perspective of boiler, whereas the maximum limit typically comes from the perspective of turbine. Now, what are these boiler and turbine considerations? Typical boiler, if it has to generate or heat up or sort of warm itself up to generate real power so that steam can be generated, the temperature beyond which a boiler should not cool down below is usually specified from operational perspective. So, the boiler tends to cool down below a particular temperature. It's as good as the thermal power plant has become non-operational, and it would take few hours to few days to again warm up the boiler to sort of generate the corresponding steam for power generation. So, for operational perspective, the boiler temperature specifically, or boiler operational temperature, decides what is the minimum limit which generator can generate or should generate, and turbine beyond a particular being a mechanical device, so turbine beyond a particular speed or particular power cannot deliver more mechanical power to the generator. So, the turbine limitation in a way also dictates the corresponding maximum real power which can be extracted from this synchronous generator. So, for our sake of discussion, we will assume this cost to be a smooth continuous curve, and often in literature this cost has been considered to be a quadratic function of the real power output P. In some context, this cost can also be considered as a linear cost depending on the type of application. Before we go deep into the economic dispatch perspective, let's understand a bit about how do we go about maintaining system economics. So, let's say we consider a function f of x, where f is the function, x is the corresponding argument of the function. F is continuous and we assume it to be at least twice differentiable. That means if fx exists, then f prime x, which is also df by dx, this will also exist, and its double derivative also exists. That means d square f by dx square, they are continuous functions, their values are well defined for all values of x. And we want to find the value of x where f takes its minimum possible value. So, how do we go about doing that? Let's take a typical function f of x. I have just taken up, sort of plotted it here. Typically, if this is my f of x, then if f of x is known and I have to sort of also see what is f dash x or f double dash x. So let me rewrite it again. F prime x, it is nothing but the first derivative of function f of x by x itself. So if we think about what is this df by dx from the first principles of calculus, df by dx is nothing but the slope of function f at different values of x. So let's say we focus on this blue part of f of x. If we try to choose one particular point, which is let's say point number a, which can also be associated or marked over here, let's say point number a, and from A we tend to move along the curve. So let's say we tend to move downward the curve. If now I have to draw a line or a tangent at this point A along the function f, then this tangent is nothing but df by dx. Since the function value is decreasing along from point A along the tangent df by dx, so basically the slope of the function is negative, and that's the reason why for this blue curve the corresponding f prime value or f dash value is also negative. This negative keeps on happening till function value at this particular point, let's say point number b, becomes or reaches its least possible value. And if I now try to draw a slope or a tangent at this point b for function f of x, this tangent will have a value or a slope equal to 0. Basically means df by dx would be 0. So that's the reason where point b is over here. And similarly from b to d, let's say this is point c, at point c and d, the curve, the first derivative tends to take a maximum value, and again at point number d, the slope is again 0. So if we continue this logic, we have 3 points among A to F where the slope or df by dx is becoming 0. So from first principles of calculus, in order to find the value of x where f takes its minimum value, what we do is, since the minimum of f of x is either at point b, it could be either at point f, also df by dx tends to be 0 at point number d also. So the first principle of calculus says, take the first derivative of function f, equate it to 0, solve this function, find its root, we will likely be able to find our x star at which f becomes minimum. Now, as I have mentioned, point B and F are the points where f is taking its minimum value. Point D appears to be a point where f is tending to take a maximum value among the local neighborhood of the points around D, or B and F are minimum in the local neighborhood of points around B and F. If we now take the double derivative or try to understand how the double derivative would look like f of x or f prime x is the slope of f of x at different points. The double derivative function is nothing but the slope of different points of f prime x at different instances. So if we, let's say, mark points A, B, C, D, the 6 points that we have, let's say around f, the way we try to find slope values of f of x at different points, let's also try to find the slope values of f prime x at different points. If we look at point number C and point number E, double derivative, which is the slope along this line for f prime x, at C and E, the corresponding f prime or double prime f double dash value, let's say if this is f double prime x, on x-axis we have x, all these are x values. The f double prime value is taking a value of 0 at points C and E. And in between C and E at point number D, the function value is decreasing. So basically if I draw the slope, which is the f prime value, C to E, the double prime value would be a negative value because the slope here is negative. So the slope typically would have a negative value. It would have a lower peak at point D where it is having a 0 crossing. And from E to F, the curve is increasing. So the slope is also increasing. So basically it would look something like this along C to F. And between C to A, which I have sort of missed here, between C to A, the slope is again increasing. So basically around point F, it would have a dip, and from B to A, it would look something like this. So double prime x, which is the slope along this point. So over here, now if we see, if f double prime x is the slope of f prime x at point C and F, where f prime x was 0, at point B and F, the double prime value is positive. So here this value is positive, here it is positive, where at D, where the value was taking its maximum around neighborhood of x, the value here of double prime is negative. So if we apply this first principle logic, this is a standard way of finding the minimum or maximum points. At x star value, where the double derivative is positive, it would refer to a minima point. Again, this all refers to local minima. There is a difference between local and global minima. All these first principles will always give us the local minima or maxima points. For global minima, maxima, there are certain additional conditions which are beyond the scope of current discussion. If the double prime value is negative, x star refers to a maximum point, and if f prime is again 0, like the first derivative, we call it to be a saddle point. Our point of interest from economics perspective is to ensure this particular condition when we have a cost function which is denoted by f of x. So what we do is, we have economic dispatch problem where there are n units. They are all connected across the same fictitious bus, boiler, turbine, generators, they are marked. And each of these generators, they have their individual cost curves. Usually these cost curves tend to be quadratic functions of f of g. And the idea is that all these generations together should satisfy the common load P of D, which is connected over here. And each of these generators should be respecting their respective minimum and maximum limits. So what do we do? How do we solving this problem? In the unconstrained form, there were no constraints involved. Whereas in economic dispatch, we also have additional constraints. We call this to be equality constraint, whereas this constraint becomes inequality constraint. So how do we go about solving or handling these inequality constraints in a optimization problem? So basically, we're talking about constrained optimization. So what we do is, we try to find an unconstrained function which is equivalent to this constraint problem. So what we do is, we focus for time being only on the equality constraint, which is ensuring total generation should be equal to total load. And for time being, we ignore the inequality constraint. So we will handle them separately. And when we try to append the equality constraint with the overall cost function, which is f of t, there has to be some scalar or some variable, because remember, the unit of f of t is typically in dollar or rupees per hour, whereas the unit of this equality constraint is typically in megawatt or per unit. So if we have to combine rupees with megawatt or per unit, there has to be some variable or some multiplier which should handle this change in unit, and that's where the variable or term lambda comes in. Similar notion could also be done for inequality, but we'll be not considering them as of now. So this function here is representing an unconstrained form of the actual constrained form, and L comes from the term known as the Lagrange or the Lagrange function. In this Lagrange function, there are two sets of variables. One is the variable lambda, and the other is generation of each ith unit. And if this is equal to the Lagrange function, this can also be considered to be equivalent to f of x in the previous slide, where x is lambda or PGI for each ith unit. So the way we applied the first order condition there, the similar logic could also be applied here. So if we do that, we come up with our first order optimality conditions. So we have, since two variables or two sets of variables, the first derivative with respect to PGI gives us this equation here, and the second, being the lambda variable, gives us our usual power balance equation. What we see here is that we have n plus 1 variables, n PGs as unknowns, and 1 lambda as unknown. So we have n plus 1 unknowns, we have n plus 1 equations, all our cost curves, they are smooth, continuous, differentiable. So n plus 1 equations, n plus 1 variables, we can easily solve them and get our solution. And these equations, they also have a good name known as coordination equations. Essentially, lambda is defining the incremental cost of supplying any additional change in load over and above the current demand PD. Now, all is good as long as the solution of these n plus 1 coordination equations automatically satisfy the generation limits. There is no guarantee that these solution of coordination equations would ensure satisfaction of generation limits. So, what do we do about then? If a generator happens to be generating within its minimum and maximum limit, that's where the simple curves come in. As per coordination equation, which is the one over here, this should always be true. But if suppose there's a generator whose generation happens to be violating the lower limit, or actual generators should not violate their limit. So suppose there's a generator whose generation happens to be lesser than the corresponding lower limit, then what should be the case? What we would observe or what we should understand here is that why this generator is generating power less than its minimum limits. It is probably generating power lesser than its minimum limit is because it is most likely a costlier generator. If it would have been a cheaper generator for a given load, it would have tried to generate as much as possible so as to ensure least cost of generation for the entire network. It is typically a costlier generator, so its incremental cost of generation, which is indicated by this first derivative, is more than the current value of incremental supply of load. If it would have been a cheaper generator, it would not have generated beyond its lower limit. Same goes well for the case when a generator tends to generate more than the maximum limit. It is most likely the case that this generator is a very cheaper unit, and hence its marginal cost of generation, which is the first derivative, is lesser than the actual cost of supplying the incremental cost of load. If it would have been costlier, then it would not have gone beyond its maximum limit. There are other counter ways of explaining or understanding how these relationships should come in, but I believe I have given my best to simply explain you all why these units or why these relationships should hold true. So this gives us a clue of how inequality constraints can be checked. So how do we do about that? Slide here presents a simple flow process. Solve n plus 1 coordination equations for n plus 1 unknowns without considering limits. If the limits, they happen to be within boundaries or limits, the solution has been obtained and nothing needs to be done. But most of the case it won't happen. So what you do is you figure out the generators which are violating their minimum limits, call that set of generators to be small p. Figure out generators which are trying to violate their minimum limit, call that set of generator to be q. So basically p refers to generators which are tending to violate their maximum limit. Q refers to set of generators which are trying to violate their corresponding minimum limit. Evaluate these violations which are shown over here or encircled over here, and then evaluate delta H. So basically delta H is a measure of how much is the deviation in respective generators violating their respective maximum or minimum limits. If delta H is positive, which means there are more generators which are violating their maximum limit, so let's first reset these generators to their maximum limit because violation should not happen. If delta H is negative at a given point of time, it would mean more generators are trying to violate their minimum limit, so we reset them to the minimum limit. If delta is H perfectly 0, we can set the respective generators at the respective limit. Once the generators are set at their respective limits, these thermal units, they are out of the economic dispatch problem. So the coordination equations, they tend to reduce because generations are being fixed at their limits. Economics is no more applicable for them. We again resolve a new economic dispatch with new load as the original load minus generators which are frozen at their limits. So they basically tend to minimize the overall load. We resolve the ED problem, come back again to step 2 and repeat this till all violations are gone. I'll just conclude this discussion with a simple example. There are 3 units which are present in a given power plant. The corresponding quadratic cost curves are given, the respective generation limits are given, and you have to solve economic dispatch for total load of 800 megawatts. So what we do, so basically we would have 3 PGs which as unknowns, PG1, PG2 and PG3 as the 3 generations, and we also have unknown lambda, which is the incremental cost of supplying the load. So for 4 unknowns, we figure out our 4 coordination equations which are shown over here. We solve them, and what happens that when we solve them, we can see that generation number 1 and generation number 3, they are not within their limits. Generation 1 is violating its maximum limit. Generation 3 is violating its minimum limit. Generation 2 is in between the limits. So basically, we have a case where solution is still not obtained. So what we do, we find delta H. PG1 is violating its maximum limit, PG3 is violating minimum limit, so we find delta H. Delta H turns out to be positive, so we first set PG1 at its maximum value. Once generation PG1 is at its maximum value, the total load was actually 800 megawatt. PG1 is frozen at 300 megawatt. So essentially, the new load is 500 megawatt, which is 800 minus 300. For 400 megawatt, we again resolve our economic dispatch while not considering unit 1 to be part of economic dispatch. We are only left with 2 units. PG2, PG3 are variable, lambda is a new variable, and new demand is 500. We resolve these for 3 unknowns, and for this, it happens that PG1 is 300 megawatt, PG2 and PG3, they are within their limits. Total cost of generation is 7559.91 rupees per hour. Optimal solution has been obtained. And we can also check this condition that when PG1 was violating its limit, the generation 1 being costlier, its incremental unit or supply is actually lesser than the current lambda, which is 9.364 megawatt, while for other 2 generators which are within their limit, their incremental cost of generation is same as the incremental cost of supplying the load. In the next lecture, we will take up the last aspect of parallel operation of synchronous generators, which would be the last part of module number 3. Thank you.